For Karen and Jim, we have a mass, and then going up is the force tension in the rope. Karen using her dynamic rope, and Jim using his static rope. And then going down is the force of gravity, or mg. We know that the final velocity is going to be square root of 2gh. So this is simply be equal to 2 times 9.8 times the height of the drop, so 2 meters, and then this will equal 6.26 meters per second. We need to find the acceleration. So acceleration is equal to velocity final squared minus velocity initial squared divided by 2 times the height. And this will equal, we know that the final velocity is 0, so we can simply say negative 6.26 squared divided by 2 times 2, the height, or rather delta y is going to be 1 meter, rather, because this is going to be, the height is essentially the height of the drop. Here, it's better to call it actually delta y, because delta y specifically is after she hits the ground. So essentially, after Jim or Karen hit the ground, their bodies essentially compress 1 meter. So they can either be bending their knees or bending their knees or rolling or anything in order to increase that delta y, because increasing the delta y will allow you to have a lower acceleration or a lower deceleration in this case, and then that will in turn reduce the amount of force that is felt by the climber themselves. So this will be equal to negative 19.6 meters per second squared. We know that sigma Fy equals MAY, and we can say that this is going to be equal to mg minus force tension. So force tension, or force of the rope, divided by mg is simply going to be equal to mg minus MAY divided by mg. M's cancel out, and then this is giving us 9.8 minus negative 19.6 divided by 9.8, and this is giving us 3. So essentially the rope holds 3 times her weight. Again, this is for Karen. So the rope can hold 3 times her weight. However, this factor of 3 represents essentially the degree in which she's feeling the drop, essentially. So the higher the number, the higher the ratio, the more force that is felt by the climber themselves. So here, 3, this is not too bad in the sense that one would be able to quote handle it. And essentially, I don't know, bones wouldn't be broken given this given this force tension. However, we have next we have Jim's rope. Now Jim's rope is static, and his delta y for the rope is 0.30 meters. So here the delta y is 1 meter, and that was due to the elasticity of the rope, how much the rope was stretching. If Karen bent her knees as she was hitting the ground, a lot of factors can contribute to this delta y. However, with Jim's static rope that doesn't stretch as much, we have a delta y of 0.30 meters. So here, F rope divided by mg is going to be, again, g minus a divided by g. And then here, this is going to equal 9.8 and then plus 6. .26 squared divided by 2 times 0.3, all divided by 9.8, and we are getting this is equal to 7.7. So this would be 7.7 times his weight. However, here the greater the number, the more likely, the more chance for injury. So here, Jim is much more likely to be injured. Force net on his body is relatively high. And that would be the end of the solution. Thank you for watching.